Video for chapter 8, I just want to kind of go over the general strategy that we're going to use to finish out this course in the next few chapters. Generally, what we're going to be given is a linear equation with constant coefficients. So we're going to have some equation L of y equals phi of x. So I'm kind of skipping down here. Don't worry about y sub p in this case, but just we have some equation and we have a bunch of initial or boundary conditions. The strategy is broken down into parts in order to first construct the general solution and then use the initial and boundary conditions to find the exact values of those constants. So the first step we're going to do is ignore what the right side of the equation is and just look at our linear differential operator and set it equal to 0. We're just going to look at the easier homogeneous equation and we're going to solve that. All right. So we talked about in the previous video that we did a simple example where we were able to solve such an equation. And in that case, we actually had an initial value problem, and we could go ahead and solve it there without doing anything else because we didn't care to solve a more complicated equation where the right-hand side isn't 0. So, but in general, we will have this right-hand side, or this function phi of x on the right side of our equation. So the first thing we need to do is just ignore that function and solve the easier problem. And when we solve this easier problem, we're going to obtain n independent solutions. Just like in the previous video, we did a second order and we were able to find 2 independent solutions. And that's always going to be the case. You're always going to be able to find the same number of independent solutions as the order of the equation. And it's actually very easy to do. And we'll see that coming up in the next chapter. Really, all it comes down to is identifying a certain polynomial and then finding the roots of it. So when does that polynomial equal 0? What inputs? Those numbers are going to tell you how to define these functions, y1 through yn. It's very simple, and you can use a computer to find all the real and complex roots of the polynomial. But we have to interpret those numbers correctly, and that's what we're going to do in the rest of the course. So that's what our first step is always going to be, is solve that simpler problem, the homogeneous problem, to find a general solution, which we're calling y sub h, which is just a linear combination of these solutions that we're going to find. So all of these functions, if we plug them into our L, give us 0. So any combination of them will also give us 0. The next step is then try to find just one example. Try to find one solution that actually does solve the harder problem where the right side is not 0. We're going to talk about a technique called the method of undetermined coefficients. Basically what it's going to be is, by looking at what phi of x looks like, we can take an educated guess as to a general form of what a solution would look like, and then plug it into L. And then we plug it into L and we compare what we get with what we have for phi of x. And using linear independence of terms, we match up the like terms and match up the coefficients. And then we can actually figure out exactly what that function must be. So again, we're going to be solving a system of equations again for numbers. But that will actually determine an exact function, y sub p, which gives us a solution to this. Once we have that, we combine that linear combination that solved the homogeneous problem with unknown constants c1 through cn with some exact function y sub p that we found in step 2. By adding those together and defining this as y, our general solution, it is a general solution. If we plug this into L, the first part will turn to 0. This all just L of all of this is 0, and then L of this y sub p is the right-hand side that we want. So this is a solution, but it has this part to it with these constants which we need in order to plug this function in to all n initial or boundary conditions, and that'll set up another system of equations that will allow us to find these constants, c1, c2, and so on. So just kind of go over this again. We're going to solve the homogeneous problem to find a general solution, which looks like this, which is called y sub h. And then we're going to use another technique to find one solution of the general equation, call it y sub p, and then we add those together to get our general solution of the entire problem. Then we plug this into the initial and boundary conditions to find out what those constants C1, C2, etc. are. So let's just look at a very simple example of this process, even though we haven't learned the process yet. That's what we're going to be doing next. So we just want to find a general solution of this non-homogeneous problem. It's a second order linear equation with constant coefficients, and it's not homogeneous because the right-hand side is not 0. So again, going to that process that we said, let's solve the homogeneous equation. We want to look for functions, two functions, y1 and y2, such that when we take their second derivative and add that to itself, you get 0. Well, that's very easy. We've seen this before in this class. The sine and cosine functions do that. The second derivative of sine is just negative sine, and the second derivative of cosine is negative cosine. So those are two independent solutions because the sine x is not a constant times cosine x, and cosine x is not a constant times sine x. So these are two independent functions, and they do solve the homogeneous equation. So we know that that gives us a linear combination of those two functions is what we call y sub h. That's our solution to the homogeneous part. Now we just need to find the other part. So then we can look at the general equation and we say, oh, I want a particular function. When I take its second derivative and add it to itself, I get 2 times e to the x. Well, again, just by thinking about this for a little bit, e to the x is its own derivative, which means it's also its own second derivative and third derivative. So if I let yp be e to the x, then of course this is satisfied because I just have e to the x plus e to the x. That's 2 e to the x. So that allows us now, we found this general solution of the homogeneous problem. We've added to that a particular solution to the general problem where the right-hand side is not 0. So this is our general solution y. At this point, if we're given initial conditions like we have here, we just take this function and plug them in. So if y of 0 equals 2, what does that mean? It means c1 cosine 0 plus c2 sine 0 plus e to the 0 has to equal 2. Well, that simplifies to c1 plus 1 equals 2, or c1 equals 1. And then the second condition, the derivative at 0 is negative 1. Well, I have to differentiate y. If I differentiate y, I'm going to get c1 times negative sine of x plus c2 cosine of x plus e to the x. I take that function, I plug in 0, and I get c2 plus 1 equals the negative 1, which is what's in the condition. And then that tells me c2 is negative 2. So again, this is a very contrived example to be very simple. This step in the problem could give you two equations, and both equations could have c1 and c2 in them. But it's just a system of linear equations. So again, you can use a computer to do that and solve and get the solutions, like Wolfram Alpha or something. In this case, each equation actually told us one of the values, so it's easier. By taking those two numbers, 1 and negative 2, we just plug them in. 1 here and negative 2 here. And we get our exact solution to the initial value problem. That's what we're going to be doing for the rest of the course. Taking a general nth order linear equation with constant coefficients, find the solution to the homogeneous problem, which has all those constants in it, c1, c2, and so on, depending on the order of the equation. And then we're going to find a particular solution. We're not going to just be able to guess it, though. We're going to have to take an educated guess at a general form of that, what that's going to look like. And then we're going to plug it into the equation and then basically force the unknowns in that guess, which is going to have unknown constants in it, different from the C1, C2, and so on. It's a separate problem. So in a lot of these problems, we're actually going to have to solve two systems of equations. One system of equation is going to help us determine what this y sub p function is, and then the other system of equation is going to help us find what the constants c1 and c2 and so on are.